Hi everybody. Thanks for tuning in today. Yeah, I'm going to present our work on scaling Istio with auto-generated sidecars. So a little bit about myself. I'm Cathal. I've been with Workday for 3.5 years, always in the public cloud team, where we manage all aspects of Workday's public cloud offering. So that's the Kubernetes platform itself, service mesh, domain-specific operators, and everything in between. I'll touch briefly on our scale, walk you through our journey with Istio briefly, some of the problems we encountered as we rolled out to our larger clusters, and how we use sidecars to overcome those problems. So we've been running Kubernetes since 1.2, currently on 121, and Istio since 1.1, currently on 111. We've had Istio running in production since October last year. Historically, we used a combination of Linkerd and S-tunnel to encrypt HTTP and TLS or TCP traffic. Our org itself, we're split between Dublin, Ireland and Pleasanton, California. I think we have about 50 engineers and 6 teams. Some teams are actually transatlantic, including my own, consists of myself, 6 others, and we're focused entirely on all things Istio. So we've 18 live public cloud production clusters across the world, plus our own data centers. The largest of which has about 4,000 pods, 300 nodes, and 70 namespaces. At any one time, we can have up to 200 dev clusters, each with about 1,000 pods, up to 1,000 pods, 40 nodes, and 75 namespaces. Namespaces are going to crop up a few times in this talk, and there is a reason for that. I know namespaces are not typically a scaling constraint for Istio, so I will explain what's going on there. So with a bit of digging, I found the first mention of Istio in our ticket system as far back as November. We had some Linkerd memory issue, and we ultimately fixed that, and we didn't roll out with Istio at that time, but it was kind of it was on the horizon from that point. By July, we had a requirement to run with low TTL certs on our workloads with a cert rotation mechanism with 0 tolerance for service disruption. So we decided to split our delivery between Istio Ingress and Istio Mesh, and we set Ingress as our first goal. So up to this point, we were using Ingress LBs external to the cluster, and we decided we wanted to run with Istio at the edge. So by January, development under full swing. We're building images off scratch or distroless for proxy v2. And we're fitting that, enormous Helm chart that Istio used to provide into our platform CI/CD system. There it is in all its glory. Hopefully not too many of you had to work with that back in the time. Come April, we had our first service using Ingress and Dev, and we had the Istio control plane rolled out to all Dev clusters with sidecar injection disabled. By September, majority of Ingress services migrated over in Dev. Istio control plane running live in production, and Istio is handling Ingress for a single service, which is a big milestone. By March, I think most services were running Istio Ingress at this stage. Excuse me. And then by January, we had pretty much everything. So Istio Ingress was running actually live in production, and we had the majority of services onboarded to Istio Mesh. There is like a good 10-month gap there that it took us to onboard everything to Istio, teaching teams why we're bringing the tech in, the problems it solves, etc., and actually onboarding them. So that onboarding involved about 180 services from, I guess, 50 or 60 teams, and that was enough of a challenge to inspire talk of its own, maybe another day. But anyway, by January, we had all services onboarded in Dev, and we began our rollout to production. So around that time in February, we were scaling up our perf clusters to match our largest production clusters to make sure everything was performant and good in the world. And unfortunately, we found it wasn't. Istio was running fine in Dev and our much smaller production environments, but it came crashing down rather spectacularly in our large perf clusters. So we have 2 kind of large clusters in particular, which are significantly larger than the others. So we paused our production rollout at this point while we figured out what was going on. Fast forward to October, mesh was rolled out everywhere in dev production, and that's where we are today. And so this talk is kind of going to focus in on the problems we had between April and October, getting those last largest clusters enabled with mesh. So as we scaled our clusters up to around 3,500, 4,000 pods, we started encountering problems with Istio. Istio-D's HBA would scale as far as it could. Istio-D pods would begin OOMing. And as a result, every data plane proxy in the mesh would start timing out, trying to pull configuration from the control plane. And those which did manage to come up, they didn't last long. Main application containers would crash because their networking was screwed and their downstream dependencies were never satisfied. So you've got crash loops going all over throughout the mesh. And this is sending wave after wave of events to the control plane to process. And the control plane wasn't processing these fast enough, causing data plane configs to time out, to slow down, causing more crashing. And we ended up with a positive feedback loop, which was essentially killing the Istio control plane, and in fact, the Kubernetes control plane too. So the first protocol was stabling Istio-D. We scaled it massively, horizontally and vertically, just to see, I guess, see if we could get it under control. We increased data plane memory to 3 gigs. Bear in mind, you've got up to 4,000 pods running 3 gigs at least. And that wasn't enough data plane, it's still OOM all over the place. We played around with pilot debound settings after max to try and reduce the amount and frequency of config pushes from the control plane. But ultimately nothing worked. Here is a snapshot of our control plane. You can see the amount of replicas we have. And these are peaking at around 8 gigs. And CPU, same again. We're running 12 CPUs, and no matter what we get, essentially, no matter what we scale to, the control plane would max out, and we were stuck with the issues we had. Now this graph here shows the max proxy memory per namespace, and we're looking at this on a per namespace again for a reason, which we'll circle back to. The worst offender in one namespace there in purple was maxing out at 8.5 gigs of memory for a single proxy. And the average in that namespace was 5.6 gigs. That namespace in particular was holding, shared messaging systems, so Kafka's and RMQ. And we noticed that those high traffic systems would have the highest memory footprint. We saw an enormous, ultimately, reduction in that memory as we introduced Sidecars, but pretty insane memory usage across the board. Majority of namespaces maxing out at around 3 gigs again, which is our limit at the time. So, Sidecars. Let's take an imaginary cluster. This imaginary cluster where blue boxes represent namespaces and green circles are pods or workloads. By default, Istio provides every workload proxy with the configuration needed to communicate with every other workload in the mesh, which is fine for a cluster with 3 namespaces and 7, 8 pods. But what happens when you have a lot of namespaces and 1,000 pods or 5,000 or 10,000 pods, etc.? This requires a pretty enormous amount of configuration to manage. It takes a lot of memory to store. It takes a lot of CPU to compute. And in reality, in a typical microservice architecture, most services only ever speak to a very small subset of all their peers. They don't actually need to speak to everybody. So what if we constrain the configuration being pushed to each workload so they only had the configuration to speak to those who they needed to? So we're essentially trying to move from the cluster on the left to the cluster on the right. So of course, Istio does have a mechanism to do this, and that is Sidecars. It's a very simple Istio CRD. It has a workload selector to select who it applies to. You get an ingress listener list, an egress listener list, and an outbound traffic policy. We won't talk about traffic policy today. It's not important here. But essentially, among other things, sidecars allow us to limit the amount of configuration pushed to our sidecars. Ingress configuration is actually derived from workload information. So your pod ports, your service ports, the services themselves. which is fine. It's pretty minimal anyway. But egress is where we really want to focus on. We can configure what downstream or upstream clusters we want to get configuration for, essentially. So we need a definitive list of all the peers that we might speak to, which leads us to one important question: who does our service talk to? Who does any given service talk to? And more importantly, as a cluster administrator, how do you get that information for 200 odd unique services running in your cluster which you don't even own? So yeah, quick note on sidecar workloads selectors themselves. A default sidecar is one with no workload selector, typically called default, sits in a namespace, and it applies to all workloads in that namespace, which aren't matched by any other sidecar. Undefined behavior occurs when a workload is assigned more than one sidecar config. So whether that's from multiple default sidecars or multiple sidecars with workload selectors. Avoid it, don't do it, stay away from it. One workload config per workload. So back to that question, who does my service talk to, or who does any service talk to? We needed some definitive source which described relationships between all services. Which, you would think only service teams could know that. Why would we know that? But we're on a deadline. Everyone's on a deadline. We're not about to approach 60 odd service teams and ask them to write a sidecar definition for every one of their services. Oh, and by the way, if you get it slightly wrong, you're going to risk breaking network connectivity. So that wasn't going to happen. We had to provide a solution ourselves. Workday internally, we have a tool called Workday Registry, which is like a who's who of services in Workday. You've got service owners, deployment platforms, dependencies with peers, etc., etc. But that has its own problems. It's manually configured, so everything is from human input. So if I build a new feature and I have a new dependency and I don't bother putting it in a work registry, well, that's not going to be accounted for. I'm going to have no network. It's not exhaustive, so it's typically used to describe, application relationships, relationships your services need to drive application behavior. It doesn't typically include things like logging syncs or metric servers, etc. So we needed something that was exhaustive, and also registry. This predates kind of Workday's adventures into Kubernetes and cloud, public cloud, and everything. So it had no concept of namespaces or services, etc. So we needed an API. We needed something with a programmable interface and something that was cluster aware. And we realized, look, network policies. We run network policies in all our clusters, of course, and we run a deny ingress by default set of policies, which means anybody, all pod-to-pod traffic in a cluster has to be described by some network policy somewhere. Furthermore, all our network policies are audited by security, so we felt it was safe to consider network policies as a canonical source of truth for all traffic flows in our clusters. Here's a sample Netcall, which we apply to each namespace. This is our default deny. So we figured if we could map out every possible allowed traffic flow from network policies, we could kind of invert that into a map of egresses, sorry. So everybody's network policies describes what services are allowed ingress to them. So we could use that to find out where services can egress. So as a start, we want to programmatically generate something like this. This is a sidecar. It's a default sidecar. Note there's no workload selector. So it applies to everything in the A namespace. And what we're doing is specifying a list of hosts which wildcard to other namespaces. So we're saying everything in namespace A is going to be able to speak to everything in B, C, default, E, and F. And in doing this, we're reducing our peer space from the entire cluster to just these namespaces. Yes, everything in those namespaces, but it's still a massive reduction. And the algorithm is very simple to do that. For every network policy in your cluster, note the destination in blue, and note your source namespaces in orange there. So kind of that's a flow from a source to a destination, add that to your map. And here's the same thing again with a pretty picture. If for every network policy peer, if it doesn't have a namespace selector, then the source is the current namespace. If the namespace selector is open, add that NetPols namespace as a destination for all namespaces in the cluster. Otherwise, add the NetPols namespace as a destination for whatever is selected by the namespace. There's a few gotchas here. If the ingress peer list is empty or missing, the rule actually allows all traffic. If the ingress peer list has no namespace selector, matches the current namespace. If the namespace selector exists but is empty, it matches all namespace. And it's really important to get this right. Again, without it, you're you risk breaking network connectivity in your cluster. Now, a note on namespaces. We've been talking about these a number of times, and here's why. Here's a Grafana snapshot I took, which shows the number of pods we have running in each of our namespaces. We have over 3,000 pods in our default namespace, almost triple the number of pods in the next target namespace, largest namespace. The impact here is that any namespace which has to egress to any service in the default namespace is going to receive configuration to egress to everything in the default namespace. And why do we have a setup like this? It's the results of decisions from very early in our Kubernetes journey. This is not good practice. It's not something you should try to replicate. Provide good namespace isolation between all of your services, and certainly we don't allow that today. But this is the reality. This is what we had to build around. So per namespace sidecars were not going to be enough for us. Looking back at those sidecars, we wanted to go a step further and define exactly which host a given namespace might want to egress to. So this means that a namespace which only wants to egress to one or two services in that default namespace is only going to get a configuration for those two. So we've gone from wildcarding on every namespace to specifying exact services in those namespaces. The biggest problem with this is that Sidecar egress listeners use FQDNs, while network policies use pod selectors. So we needed some way to find what services sit in front of a given pod. Kubernetes provides no such mechanism to do that. There is no way natively to find which services may sit in front of a given pod. So, of course, Kubernetes services use pod selectors to select pods, and that's very straightforward. That's a one-way lookup. And network policies, our source of truth, can select pods via different pod selectors to services. So the question is, if you're given a pod or a pod selector, how do you discover which services may sit in front of that pod? And actually, it's quite easy. So a pod selector gives us a label selector, and all that's doing is listing pods in a namespace and reducing them to those whose labels are a superset of the label selector. So similarly then, we take those pod labels and we list all services in that namespace whose pod selector is a subset of our pod labels. So we need to adjust our algorithm very slightly. Instead of mapping to destination namespaces, we're just going to map to destination services using the method we just described. The problem with this now is we were generating these kind of as we bootstrapped our clusters. So they weren't very, they weren't dynamic. Of course, clusters are not static. Namespaces change, services, pods, network policies, they all change. And these sidecar definitions needed to respond and be regenerated accordingly. We needed something dynamic. Introducing the Sidecar Generator, very appropriately named, it generates Istio sidecars. It's an evolution of what we've just seen before. Rather than running, during cluster bootstrap, we actually run it in a cluster permanently as a deployment. It's long-lived. So it watches namespaces, services, pods, and network policies, and responds to those changes and regenerates sidecars live in the cluster. So we're scribed to interested resource events using a shared informer. The shared informer triggers add, update, and delete functions. We do a bit of filtering there to ignore events that we don't care about. For example, annotation changes they're not going to impact our sidecars, so we don't care. Event handlers decide whether or not they need to trigger a regen of sidecars. We essentially, push these events into a channel of one size. If there's something in the channel, regenerate the sidecars. Take the item from the channel. Otherwise, wait. And this is the output. Yeah, it's a bit blurred. But yeah, imagine this with a couple hundred sidecars, and you're creating this for every namespace in the cluster. Yeah, and this had pretty enormous impact in our perf clusters. It completely stabilized the Kubernetes control plane, Istio control plane. You can see the worst offending max memory per namespace has dropped from 8.9 gigs to 1.3. That's an 85% decrease. The worst offending average memory, average memory per namespace has decreased from 5.6 gigs to 650 megs. That's an 88% decrease. So absolutely enormous memory decrease in the data plane. And something similar in the control plane. And the top graph here is CPU per Istio D instance. We saw a 75% reduction there. And the bottom is the same for memory. We saw approximately 66% reduction in memory. And also at a fraction of the number of replicas. This is actually a sane number of replicas. I think we had 6. Probably could scale down even further. So yeah, that's pretty much it. Moving forward, as we scale our clusters, we're probably going to have to optimize even further here again. We were generating sidecars per service. We could go even further and generate them per service per port. The sidecar allows us to do that. I don't know if we're going to see huge optimization there. I don't know. I don't think we have too many services which expose ports that aren't used by all their clients. Ideally, we would generate a single sidecar for every workload, but that requires a unique label for every single workload. We saw a pattern in our clusters where teams might use a layer label, which would select multiple unique services. Then they would also use an app or a name label to select individual ones, and that kind of screws up how you are applying workloads to individual pods. But it's something we could solve, but we haven't needed to yet. A big one for us, and it's something that we're absolutely working on since discovering this, is eliminating those shared namespaces completely. So the default one is a pretty bad example for us, and we've been pushing back on service teams heavily to do that. We did find one kind of issue upstream on the Envoy proxy Git, where people were talking about lazy loading Envoy clusters and routes and endpoints as they were kind of queried, which would be pretty awesome. The conversation seemed to die off in about March, so I'm not sure. I don't think there's any active work on that at the moment, but that would be something really awesome to see in Envoy, and obviously we would get to reap the benefits from that in Istio too. That's all for me. Open to any questions you guys have.